Although they are titled force fields, fields around objects can also be used to determine energies associated with forces. From previous study, we know that energy is force applied multiplied by the distance moved by the object in a direction of the force. Gravitational potential energy in a uniform field is given by the gravitational field strength multiplied by the mass of the object within the field multiplied by a difference in the distance from the centre of the field to the object that travels around it from start to finish. In fields studies, we can define a new property associated with forces. This property is called potential. Potential is easy to describe. An object has potential if it can do something, but it isn't yet doing it. The question becomes, how do we define this mathematically? Changes in gravitational potential energy are given by the equation mass times gravitational field strength times height. Height is the difference in distances from the centre of the field. The mass of the probe object does not change, but in our studies of fields so far, we have seen how a field strength can change and the position of the probe mass can change. That is why potential is defined as the gravitational field strength multiplied by the change in distance from the centre of the field. Gravitational field strength in a radial field is big G, big M over R squared. So potential is big G, big M over R, where R is the height. But what about the direction? How do we show the changes in gravitational potential with distance? If we look at the situation of the Earth, we can describe some useful instances. On the surface of the Earth, we feel gravity strongly. We are pulled to the centre of the Earth. If we raise an object away from the centre of the Earth, we move it away from the centre of the Earth's gravitational field. This increases the potential kinetic energy available to the mass we are lifting, but it decreases the potential for that object to fall. As we have seen, the force of gravity is determined by both magnitude of masses and the distance the masses are apart. The further away two masses are, the weaker the force is between them. If we move our object further and further away from the Earth, we must give it less and less energy to move it the same distance. The force of gravity decreases with distance squared. The problem becomes the nature of gravity. Gravity is a universal force. As far as we know, gravitational force has no limit. The mass of our planet may affect the most distant galaxy flung far across the universe. It will give a very small effect, but an effect nonetheless. This means that we have to invoke the infinity concept to give us a value for zero potential. It is only at an infinite distance from our mass that our probe mass has no potential to fall towards it. It is at this distance that the force on the probe mass is zero. Our probe mass starts at an infinite distance from our field mass and has zero potential. The mass then moves to determine distance from the field mass. It now has a determined distance, but its potential is lower than it was before. Some of the potential to generate energy has been used up in moving closer to the field mass. This means the potential is always negative. Changes in potential can be negative or positive, but the absolute value of potential is always negative unless it is infinitely far away from the field mass and so has no potential to generate energy. The field strength of this field is as described above, but now we have defined potential, we can also redefine field strength. Potential was defined as field strength times by the change in height. Rearranging this equation, we can see that field strength is now change in potential divided by change in height. For gravitational fields, we have to introduce our negative term for the reasons discussed previously, giving gravitational field strength as negative change in potential divided by change in distance from the centre of the field.